Okay, so of course, as we're looking at the equation of motion, the next step is to then move on to the other coordinate system. So x y के बाद, as we've done in kinematics, हम nt coordinates को consider करेंगे rather than the r theta. Okay, so nt and then r theta, inshallah, tomorrow. So now, as always, let's start with some examples. Now, the examples, of course, for just consists of combining kinetics, that is, जहाँ पे भी हमें the cause of the motion को analyze करना हो, with a motion जो path उसका इस किस्म का हो जिसके अंदर हमें NT coordinates use करने हो. So there is one example right here, which is when we have cars going along some curved paths. So where we know the know the curved path, then we tend to use our NT coordinates as we had discussed in kinematics. Now this example I will do in a little bit more detail later, लेकिन इसके बारे में हम अभी से सोचना शुरू करते हैं. This is basically that when we have our any car, but in particular when you have cars going at very high speeds, such as race cars, motorcycles, even Formula 1 या वो दूसरी क्या होती है वो अमरीकी जो होती है NASCAR, etc., then you might have noticed that at their turns they tend to have roads which are inclined from the horizontal. That is, इस किस्म की road को ना banked curve कहते हैं, because it's like a bank for the, जिस तरह river का एक bank होता है उस तरह. But there is actually a reason for this, which we will discover in the course of the lecture today. Okay, so this is one application of looking at NT coordinates and looking at kinetics in the NT coordinates, right? Next, let's just one example for today, and then we're going to jump into describing the coordinate system and moving officially onwards with how we perform kinetic analysis in the NT coordinates. Okay, so as before, we know, okay, if we have a known path and the particle is moving along it, then we can define two coordinates known as the normal and tangential coordinates, something like so, where the tangential coordinate is this one. It's at a tangent to the curve, and the normal coordinate, this one, n, is always, it's perpendicular to the tangential coordinates, it's normal to the tangential coordinate, and then it points towards the center of curvature of the curved path. So, for example, अगर ये curved path है तो हमारा center of curvature उसकी ये concave side की तरफ होगा, inwards. So that's why my n coordinate points like so. Okay, so these two we are familiar with, and for the NT coordinates we tend to place our origin at the particle itself. So our inertial frame of reference would be, so to speak, the Earth, and then the coordinate system, the NT coordinate system, would be placed at the particle. Now there's just one thing which is new here, which is that I'm looking at this current path in 3D. अभी हम ये पहली दफा I've started to look at the normal and tangential coordinates in 3D. And now the point is, if I look at something in 3D, then as you may all intuitively know, okay, we need three coordinates to define the position of anything in space, in 3D space. So the NT coordinates taken together define a plane. Okay? So this is our plane of motion, so to speak. But then there's also one more axis or coordinate which is outside, lying outside the plane or pointing out of the plane. This we call the, let me bring it up. We call the binormal vector. And the reason why it's binormal is because this is, of course, then perpendicular. It's normal to both the t and the n axis. Okay? So that's why it's binormal, perpendicular to two of these, right? And of course, if it's perpendicular, that basically means that if I take the cross product of n and t, I will get the binormal unit vector. And if you consider this, the अभी जो current diagram में बनाया हुआ, this is still again a right-handed coordinate system. So if you use your right hand and use your thumb, index finger, and your, what's the other one? The middle finger. And you point your, अब आगे से फिर मेरा थोड़ा घूमना शुरू हो जाता है कि if you point your fingers and your thumb in particular directions. So ये जो तीन axes है ना, they make up the directions of a right-handed coordinate system. Okay, now this is interesting because I've introduced this new binormal direction, but abhi hum very shortly we'll see whether this comes into play or not, and why have I just popped it in here today. Okay, so abhi slowly we're building that up. Right, so now if I write down my equation of motion, I think you all now know this is the equation of motion, and because I'm using the NT coordinates, then of course I can break down my resultant force and my acceleration into the respective coordinates for this NT coordinate system. Right, so the resultant force can then be broken down into its component in the tangential direction, summation ft in the ut direction, then summation fn in the normal direction, and then finally, because there is this third coordinate direction, which is my binormal direction, which I've just introduced. So then the summation of fb, so the resultant forces in the binormal direction, is also included within my resultant forces. But what the important thing that I need to remember is that my path is actually, or my motion is just occurring within the NT plane. That is, my accelerations are only going to be in my tangential and normal direction, right? Whereas this binormal direction, which I have pointing upwards, if I'm looking at any car or anything else which is moving in a curved path within this plane, then it doesn't have, it's lying within this plane, right? So it doesn't have any vertical components of acceleration such that my AB is just, it's zero. Which is why on my right hand side, I have no consideration of my acceleration in the binormal direction. Okay? So another way to think about it is that if the car is going on a turn, it's not going to jump off the ground, is it? So it's not, unless के कोई rockets नीचे लगा दें और फिर हम एक और किस्म का motion consider करना शुरू कर दें. When I'm just talking about my curved path and my plane जिसके अंदर वो curvilinear motion हो रहा है, उसके अंदर there is no vertical acceleration. Hence why there is no AB right here.
Excuse me, ma'am.
जी please.
मैम अगर एक्सेलरेशन नहीं है बी कोऑर्डिनेट की डायरेक्शन में तो फिर उसे लेने का फायदा क्या है?
फायदा क्या है? एग्जैक्टली राइट. फायदा ये है कि इवन दो उसकी एक्सेलरेशन जीरो हो, let's take the example of the car going on the curve. It still has a weight which is going to be acting in the minus b direction, and it's still going to have a normal force acting on it which is going to be acting upwards in the b direction, right? मतलब ये कि it does have forces acting in the b direction, it just has zero acceleration, which means, what does that mean? That means that this summation fb, if there's no acceleration in the b direction, then this summation fb must be equal to 0. That is, I'm saying basically that in the b direction it's a case of static, or the resultant force in the b direction is going to be 0. So I'm just including this right here ताकि हमें ये बात याद रहे कि forces हो सकती हैं, सिर्फ वो they must sum to 0 for that direction. Okay?
Okay, ma'am. Thank you.
Thank you. Okay, just another thing to point out here कि ये somebody may ask this, अभी तक कभी किसी ने कहा नहीं कि okay, मैं तो सिर्फ only examples मैं देती जा रही हूँ जिस केस में जैसे there's a car on the ground, right? So उसका curvilinear path जो है वो NT coordinates में और B में कोई acceleration नहीं है. But what if there is something जो NT curvilinear में भी जा रहा है और B direction में भी उसकी कोई acceleration? Now, that is उसका AB कोई exist करता हो. Let's say कि there's somebody वो जो चले, even the case of a rocket, sometimes it's going straight up, but sometimes they're actually going in some sort of a curvilinear motion, right? या फिर किसी भी चीज़ का अगर 3D curvilinear motion हो, फिर क्या करें? So for that, I have the answer. Luckily, for this third semester, your second year dynamics, we are not considering such complicated cases of 3D motion. But inshallah, eventually you will be doing those too when you move to mechanics of machines and so on. So tab you will consider these in much more detail, where you will use the NT coordinates, NTB coordinates in 3D, or the R theta Z coordinates in 3D. But for this course, abhi hum isko sirf we'll only consider problems jahan pe AB is 0. Okay? To make our life
अगर 3 डायमेंशन में मूव कर रहा हो
जी,
तो बाय डेफिनेशन हमारा जो एंटी और एंटी कोऑर्डिनेट होगा वो उस प्लेन में आ जाएगा, प्लेन ऑफ मोशन में, तो बी की डायरेक्शन चेंज हो जाएगी ना?
बी की डायरेक्शन चेंज होती रहेगी. यस, बी विल आल्सो
तो
कीप
बी तो हमेशा 0 रहेगा, ए बी.
गुड पॉइंट. यस. Not exactly, because what if uska, oh, that's a great point. Yes, could always be, because we keep changing the t and the n. Oh yes, I hadn't thought about it. Thank you so much. Who is speaking right now?
शर्जील.
Shurjeel, thank you. Yes, Shurjeel, आप बिल्कुल सही कह रहे हैं. Okay, Shurjeel is saying कि even अगर वो 3D space में भी हो, let me draw out an x, y, z coordinate. Oh, मेरी x, y, z भी थोड़े उल्टे सीधे हो गए. अगर z ऊपर हो, y would be something like this. X, y, z, something like this. Or if I have a 3D path going in something, then Shurjeel is saying कि बेशक ये ऊपर नीचे z direction में move कर भी रहा हो, our nt coordinates always keep changing with the path. ठीक है? So जिस तरह nt path के हमेशा tangent and then normal ऐसा रहेगा, फिर ये मे बी vertical plane में नीचे आ रहा हो तो normal नीचे की तरफ point कर रहा हो, and tangential is like so. Then always the b also keeps pointing in a direction such that उसमें कोई acceleration होगी ही नहीं. Shurjeel, you're right. Actually, I apologize. Let me take back what I just said. कि 3D motion में AB can be non-zero. One second, let me just complete this point. So the point is, just by definition of what the NT coordinate is, that is, it's those coordinates they just follow the path and they keep changing, even if it's a 3D path. Then this B direction always has a 0 acceleration, because NT ही change ही ऐसे होते जा रहे हैं ताकि acceleration हमेशा इन्हीं दोनों के directions में define हो. Perfect. Yes, you're right, Shurjeel. Thank you. हाँ जी, क्या कह रहे थे अभी कोई और?
मैम मैं कह रहा था कि टॉर्नेडो का मोशन देखें, उसके अंदर कोई चीज एंटर होती है तो उसमें बी डायरेक्शन में भी एक्सेलरेशन होगी, क्योंकि वो अपवर्ड भी मूव कर रही है, टेंजेंशियल एक्सेलरेशन भी है सर्कुलर में, और सेंट्रीपिटल फोर्स के सेंटर में लग रही है, तो तीनों एक्सेलरेशन प्रेजेंट है.
आप उसको ना r थीटा कोऑर्डिनेट्स में सोच रहे हैं, where you're defining the r from its center. अगर nt कोऑर्डिनेट्स को देखें ना तो it doesn't matter कि वो टॉर्नेडो के अंदर, ये टॉर्नेडो है मेरा, अगर टॉर्नेडो के अंदर वो चीज यूं घूमते हुए ऊपर जा रही है नीचे जा रही है, बिकॉज nt जो है ना वो इस पाथ के रिलेटिव डिफाइन हो रहा है, नॉट रिलेटिव कि ये एक्सिस है इसका तो इस तरह यूं r होगा. नो, इट्स डिफाइंड कि अच्छा अगर ये यूं ऊपर की तरफ भी जा रहा हो तो इसका फिर नॉर्मल डायरेक्शन ये हो गई और टेंजेंशियल ये हो गई, एंड सो ऑन.
ठीक है मैम.
ठीक है जी. तो इवन 3D में भी दिस द पाथ इज द थिंग दैट द NT coordinates are following. Nice. Okay, so this is a little something to think about more carefully. So I encourage all of you to ponder over it yourself as well. See, so I completely missed it, और मैं simplistic उसमें चल रही थी कि हाँ 3D में तो yeah. So Shurjeel, thank you very much for pointing that out. Right. So AB will be 0 because the NT coordinates are they're following the path whether we're in 2D or 3D. Such that for our curvilinear motion, we're always just going to have our acceleration in the tangential and the normal directions. So we're always going to have a resultant force in the B direction, which is 0. Just be careful to note here that this NT and B coordinates are changing their directions at each point on the path, right? So अभी ये मैंने vertically upwards बनाया हुआ था, But if there is 3D motion, then this can be pointing in, it's just perpendicular to N and T. That's what's important. It's not necessarily always vertical, right? Okay. Right, so we know what that we can then break up this vector equation into three different scalar versions. So our scalar versions are just written here. So the scalar version in the tangential direction, the scalar version in the normal direction, and noting, as we've just discussed, that the resultant force in the b direction would always be 0, because there will never be acceleration in it, just by virtue of our definition of the NT coordinate. Right. Okay. So just as before, okay, that's it for the equation of motion. Aage phir comes into the kinematics aspect, which is ke maybe ye AT or AN, how do we find these? So you remember that we've already done the NT coordinates for the kinematics of the NT coordinates. So we know that hamara the tangential coordinate, it actually equal to AT is equals to V dot. That is, V dot is the change in the magnitude of the velocity. I just want to remind you of this. And that the normal component is V squared divided by rho, where this represents the change in the direction of the velocity vector. Okay, this is the change in the magnitude, and this is the change in the direction. And also noting that this the normal coordinate is always defined to be acting towards the center of curvature. So this Fn, of course, always will be acting towards the center of the path. Okay, and this is why, again, this An was always going to be pointing towards the center of curvature, and hence was known as the centripetal acceleration. Usi tarah, because Fn will always be directed to, and it always seeks the center. That's why it's known as the centripetal force, center seeking force. Perfect. Yes, finally, the rho that we need for our normal acceleration, the radius of curvature, we can get just by using calculus. We'd not derived this, but this is the result that we have. Okay, so these formulae, of course, will be provided to you. Now, let's just very quickly go over the what's the word? The procedure for the analysis. So, if we have a known curved path, then we may decide to go for the NT coordinates or even sometimes the R theta coordinates. I just want to take a very quick moment here to highlight when we would go for the NT as opposed to the R theta ones. So I think with practice this will come. Secondly, I think thoda sa just general discussion ke lihaz se, we'll go for the NT coordinates when we have just some sort of a general curvilinear motion. Okay, where it's not really moving with reference to a particular point. It's just some curvilinear motion, such that the origin, we have to keep defining the origin at each point. Even though uski initial position se hum uski position define kar rahe honge, maybe, but there's no sort of reference point that is just fixed. Whereas for the R theta coordinate, if we have a curvilinear motion, let's say which is spiraling with some sort of an increasing radius or decreasing radius or something, then I can see that this spiral does have some center somewhere which can act as my origin, and which is useful to represent as some sort of a reference point. So for this sort of curvilinear motion, जिधर कोई reference point है जिसको मैं use कर सकूं, then I tend to use my R theta coordinates. Whereas when I have just some general curvilinear motion जहाँ पे मेरे पास कोई fixed reference point नहीं है, then you use the NT coordinates. Okay. Remembering, of course, that the origin is fixed in the R theta coordinates, whereas it is not fixed in the NT coordinates. Just some side discussion right here. Perfect. Okay. So right now we're talking about the NT coordinates. So once we've done that, then of course we establish the correct positive directions for the normal and tangential coordinates according to the convention. Okay. So tangential direction is along the direction of motion, whereas the normal direction is pointing towards the center of curvature. फिर we draw, फिर kinetic वाला analysis आ जाता है, right? So we draw first the free body diagram, then we draw the kinetic diagram. Now, the interesting thing to note for the NT coordinates is कि kinetic diagram में ना it's useful for us कि हम उसका resultant acceleration ना plot करना शुरू करें. Let's say ये मेरा particle था और उसकी कोई ऐसी सी path है. What's actually useful for me, not कि मैं उसकी पूरी acceleration किसी एक resultant force से represent करूं, but instead what's useful for me is कि मैं उसकी kinetic diagram में भी उसका MAT and if थोड़ा सा tricky सा center of curvature मैंने बना लिया, लेकिन इससे कि वो inverse है, then MAN represent करूं. Why? Because the resultant acceleration doesn't really tell me much. What's actually more useful is for me to see these components. Okay, so I'm just trying to point out that kinetic diagram in the NT coordinates, we actually plot the two components of acceleration separately. Perfect. Oh yes, and of course noting here, okay, for the acceleration, the normal acceleration is always in the positive n direction, just by virtue of the definition of the n coordinate, whereas the tangential acceleration actually, वो या तो उसकी velocity could be increasing in that direction or it could be decreasing, which is why its tangential acceleration can either be in the positive tangential direction or in the minus direction में भी हो सकता है. Okay, so just some fine points right here. The tangential acceleration may act in either the positive or the negative t direction. Then we apply our equation of motion and solve if we need anything further than the acceleration, then we use our kinematic relationships. Perfect. Just pointing out here that for the tangential component, this A tangential is equals to dv by dt, right? जो हमने standard किया हुआ था for our rectilinear motion, we know that acceleration is just equal to dv by dt. तो इस case के लिए, for the tangential case, we can actually apply the same equations, kinematic equations that we had for our rectilinear motion, right? Whereas for the normal acceleration, we can't do that. For the normal acceleration, it's something special. It's telling us the rate of change of the direction, or that's given by this value right here. Okay. So any questions with the procedure or what we've discussed so far before I jump to some examples? No comments? Okay, so right, let's jump to an example then. As always, please, I need all of you to take out your pens and papers and calculators and help me solve it, or actually start solving it first yourself. Right, so we have a little, I guess, a little boy. He's sitting on a swing where, of course, when you're swinging, you're going to go along some sort of a curvilinear path, right? And what's happening is that at this instant, this theta is equals to 60 degrees, and the boy's center of mass G is momentarily at rest when theta is 60. मतलब अपने highest point पे पहुंचता है. Then the boy has a weight of 60 pounds. Neglect his size and the mass of the seat and the cable. And what we want to find is the boy's speed and the tension in each of the two supporting chords of the swing when theta is equals to 90 degrees. Right, okay, so we're given the conditions for theta is equals to 60. His speed was, at theta is equals to 60, his speed was 0. What we want to do now is that theta is equals to 90, where we want to find the velocity and we want to find the tension in the cable. That's what we do. Okay, so let's start this problem. Or of course, yeah, I forgot to say here कि this, even though इसमें लगेगा कि एक fixed coordinate है and so on, and we can solve it using the r theta coordinates. लेकिन just to make our life a little simplified, just note कि ये हम NT coordinates के लिए एक example के तौर पे use कर रहे हैं इसे. Okay, so this is going to be my NT coordinates की example. So let's start with defining my free body diagram and so on. Okay. So let's say this is my particle who is the boy. Then this is, sorry, by the way, I'm starting with my free body diagram. Oh, pehle I should define the, sorry, I see I'm forgetting my steps. I should define the coordinate system, right? So on the particle, I'm going to define my coordinate system like so. So of course, this is the center of curvature. So this will be my UN direction. And then abhi momentarily at rest, is going to start to move down. So this will be my UT direction. Okay, so ये मेरा coordinate system is defined. Now let's come to the forces which are acting on this boy. So to draw the free body diagram, I have, of course, that there are how many cables? There are 2 cables. So there will be 2. Oops. There will be 2 times the tension here. Okay, and of course I have the I have the weight which is acting downwards on the boy. Okay, that's it, right? वो seat जो है वो तो that's sort of part of the boy's system. तो boy और seat एक combined particle बना रहे हैं. So that's why I think I've just got this. Yeah, there are no other forces. There are no external other forces acting on it. Right. So let me just get some of my geometry in there. So I know कि ये angle theta है. This angle the cables make is theta. So then this one will also be, this will be theta. Right. So just एक थोड़ी सी वो लेते हैं. इसी के ऊपर let me also, या इसी के सॉरी साइड पे let me draw my kinetic diagram, जिससे मेरे पास मेरी normal और tangential directions की accelerations clear हो जाएंगी. So I know that I will have a MAN, right, in the UN direction, and I will have a MA tangential in this direction. Or further now, I also know कि ये theta angle ये वाला है. So that is कि if I draw the horizontal like so, then this will be my angle theta. थोड़ा सा और थीटा की मुझे वो भी करने दें कि अगर मैं let me change my pen angle, pen color, sorry, pen angle. इसी के ऊपर भी let me draw my U normal and my U tangential, so that I can spot के weight जो है वो क्या angle बना रहा है with UT, so that I will be able to resolve the weight in these 2 directions. Okay, now help me figure this out कि ये angle क्या होगा, this angle. Okay,
मैम
right.
30 degrees होगा.
क्या होगा?
30 degrees.
क्या होगा? Sorry.
30 degrees.
30 डिग्री कहाँ से आ गया? मेरे पास तो थीटास चल रहे हैं. It is 30 डिग्री.
मैम थीटा 60 है ना, तो वो उन दोनों के दरमियान एंगल 30 होना चाहिए.
ओके, कौन बात करता है प्लीज?
मैम ज़ैद
देखे ना, लेकिन बात ये है कि थीटा जैसे जैसे वो बॉय स्विंग करता रहेगा, दिस थीटा इज गोइंग टू कीप चेंजिंग. इवन इनिशियली भी थीटा 60 गिवन है और फिर बाद में हमने चीजें फाइंड करनी है थीटा एट 90. So it's a good idea actually to keep it general right now as theta.
Okay.
Because it will be changing. Okay. So that's why I want you to think about के this general theta के terms में ये angle क्या है, ये blue वाला which I marked.
Theta.
Theta, yeah, exactly right. So let's think. Let me work through this. Okay. So if this angle is theta और un और ut के दरमियान में तो 90 degrees है, so this angle will be 90 minus theta right here. This is 90 minus theta और फिर of course horizontal और vertical के दरमियान में भी 90 degrees है. So of course फिर ये क्या होगा, ये 90 minus theta है, which is then of course just theta. Okay. Great. Okay, so I am getting somewhere. Now let's start to apply my equation of motion in my two directions. Let's change my color again. So of course, applying the equation of motion, I have summation f in the tangential direction is going to be equals to MAT, and simultaneously I also have that summation f n is equals to MAN. ऐसा ही है. Now let's start to solve each of these one by one. So let's say summation ft वाले को पहले करते हैं. ठीक है, तो forces in the tangential direction, I have 2t in the positive direction. So I've got my 2t right here. And then, sorry. I'm already wrong, aren't I? Tangential direction कौन सी थी? ये वाली है. Oops. This one. So टेंशन का तो कोई टेंजेंशियल डायरेक्शन है ही नहीं, right? So I apologize, I made a mistake here. No tension. Instead, what do I have in the tangential direction? It's just a component of the weight, right? Weight is acting something like so, right? In the tangential and the normal direction. So this is W in
जो
the
सीट है, उस सीट का जो रिएक्शन है उस फोर्स को कंसीडर क्यों नहीं कर रहे हम?
सीट जो है वो बॉय का ही हिस्सा है, बॉय के सिस्टम का ही हिस्सा है.
सही, ओके.
So the boy applies a sort of, मतलब समझे कि कैसे, असल में ये जो केबल है ये जाके लग, हाँ जी प्लीज.
जो सीट फोर्स लगा रही है वो टेंशन वो दोनों रस्सियों ने खींची हुई है ना ऊपर, तो हम तो वो कंसीडर आ जाएगी, उसके अंदर ही आ जाएगी.
एग्जैक्टली. हाँ चले, ये भी दैट्स अ राइट वे टू थिंक अबाउट इट, कि वो नॉर्मल फोर्स भी टेंशन की डायरेक्शन में ही एक्ट कर रही है, इसलिए उसमें कंबाइन हो जाएगी. मैं ये कह रही थी कि एक्चुअली जो इंटरैक्शन का सिस्टम है ना, वो है कि टेंशन जाके लग रही है सीट पे और फिर सीट जो है वो नॉर्मल फोर्स अप्लाई कर रही है बॉय पे. तो अगर हम अलग अलग करके देखेंगे ना तो होएगा ये कि द नॉर्मल फोर्स इज इक्वल टू द टेंशन एंड देन बॉय के ऊपर वो नॉर्मल फोर्स लग रही है. दैट्स व्हाई आई हैव जस्ट गॉट माय द टेंशन राइट देयर. ठीक है. ये थोड़ा, is that clear or not so much? I should explain it more.
Yes ma'am, हो गया.
Okay. Right, so I was resolving the weight and I was noticing it's only the weight which has a force in the tangential direction. So which I can see is my weight ka cos theta projection in the positive tangential. So it's weight cos theta. And that's it. I have no other tangential force. So just W cos theta is equals to M A tangential, or A tangential I know is V dot, right? Ab, let me also write down that W is mg. मेरे M and M cancel out and I get left with के my V dot या फिर my dV by dt is equals to mg cos theta. ठीक है. Okay, so this is useful. I've got some headway. Now let's think. Can we just, अभी हमें velocity क्योंकि find करनी थी ना. So maybe I would consider that I could just integrate this expression right here. If I integrate it, I'd find my velocity perhaps. But there's just one small issue when I try to integrate it. So if I integrate it,
M तो cancel हो गया. M को cancel कर दें.
M sorry, M cancel हो गया. Now if I try to integrate it, there's just one small issue that I end up with, which is कि okay, left hand side तो integrate हो गई with velocity 0 से लेके फिर v तक जा रही है. It's just dv की integration है, so this is v. But the issue I have right here is that I'm trying to integrate theta with respect to time, but I have no idea what theta is as a function of time. तो मैं ये इंटीग्रेशन कैसे करूं? मुझे थीटा एज अ फंक्शन ऑफ टाइम पता ही नहीं है, right? So which is why I can't actually do this integration, और इस तरीके से मुझे velocity directly नहीं मिलने लगी. So I need to think of something else. This will not.
मैम
जी
हम इस तरह कर सकते हैं कि हम s इज इक्वल्स टू r थीटा से s निकाल लें जो आर्क है आर्क लेंथ, और फिर
बिल्कुल सही कह रहे हैं. So इसी पे जरा सोचना.
थर्ड इक्वेशन ऑफ मोशन लगा के
बिल्कुल ठीक कह रहे हैं. So मसला ये हुआ है अभी हमारे पास जो पहली किनेमैटिक इक्वेशन थी जिसमें एक्सेलरेशन वेलोसिटी ऑफ टाइम रिलेट होते हैं, वो तो हमारे काम नहीं आ रही. अब और कौन सी ऐसी रिलेशनशिप है जिसमें हमारे पास एक्सेलरेशन और वेलोसिटी है? That is of course the other one that I have is at ds is equals to v dv. This is the only other kinematic equation which I've got left. वो तीन kinematic equations में से this is the only other one जिसमें acceleration भी आ रही है और velocity भी आ रही है. So it's actually this one which let's try to use this one. Okay. जैसे कि अभी आपके one of your colleagues suggested, I'm going to make a little box right here to do that. Okay, so let's implement this. AT जो है जी AT जी,
अगर हम इसके एक्सेलरेशन के वो ले लें, वो जो इक्वेशन है v स्क्वायर ओवर रो का जो सॉल्यूशन है an इज इक्वल टू v स्क्वायर ओवर रो, वहाँ से हमारे पास वेलोसिटी और इसका रिलेशन आ सकता है.
फिर से बताइएगा कौन सी इक्वेशन मैं इधर लिखूं फिर से?
मैम वो एक्सेलरेशन an इज इक्वल टू v स्क्वायर ओवर रो, वो जो मतलब एक्सेलरेशन का जो नॉर्मल कंपोनेंट का जो वो है रिलेशन, वहाँ से हम कर सकते हैं इसको.
मैंने अभी ये नॉर्मल वाला तो इधर लिखा हुआ है, मैं अभी उधर पहुंची ही नहीं थी. अच्छा ओके, आप कह रहे हैं कि पहले ये नॉर्मल वाली साइड को कर लें. ओके, लेट्स डू दैट. ठीक है, गॉट इट. One of your colleagues has suggested कि ये टेंजेंशियल वाले पे जरा पॉज लगाएं और इसको आगे चलते चलते जरा सब्र करें, इधर से ही मिल जाएगा नॉर्मल कंपोनेंट से. सो लेट्स ट्राई टू डू दैट. तो नॉर्मल कंपोनेंट की फोर्स रेजोल्यूशन करना शुरू करते हैं. अब नॉर्मल इज दिस वन, राइट, दिस वन. तो इसमें आई कैन सी आई हैव माई 2t एक्टिंग इन द प्लस डायरेक्शन, एंड देन आई हैव माई दिस वेट का एक कंपोनेंट है जो ये -wn है, विच इज -mg sin theta. And now this will be equal to m, or an is I know v squared divided by rho. ठीक है जी. अब इसको मैनिपुलेट करना शुरू करते हैं. तो इससे मेरे पास क्या आ रहा है? इससे मेरे पास आ रहा है कि इससे तो मैं अभी भी थोड़ा सा क्या कहाँ जाऊँ, मुझे टेंशन नहीं पता, मुझे थीटा इज चेंजिंग और मुझे वेलोसिटी नहीं पता. I'm still stuck actually. I don't know my tension, I don't know my theta is changing, it's a function, right? So I can't just directly jump in to substitute my values. और फिर मेरी velocity जो है वो मुझे find करनी है. तो अभी मैं फंसी हुई हूँ अभी. So for example someone could suggest to me कि मेरे पास एक तो मुझे पता है ना बाउंड्री कंडीशन कि थीटा जब 60 डिग्री है तब वेलोसिटी इज 0 है ना, ये मुझे पता है. लेकिन इशू इज कि व्हेन आई डू दिस, व्हेन आई सब्स्टिट्यूट दिस इन हियर, ऑल आई एम डूइंग इज आई एम फाइंडिंग द टेंशन एट दैट इंस्टेंट व्हेन थीटा इज इक्वल्स टू 60. इससे मुझे सिर्फ वो टेंशन मिल जाएगी. whereas what's happening in as I move along my path is this tension is changing, और मुझसे वही कहा जा रहा है, आई एम बीइंग आस्क्ड टू फाइंड इट एट 90 डिग्री. अगर मैं 90 डिग्रीज की सब्स्टिट्यूशन भी कर लूँ लेट्स से इस वाली एक्सप्रेशन में, तो तब आई एम स्टक बिकॉज आई डोंट नो व्हाट द वेलोसिटी इज. Okay? So I'm not getting any ahead by using this one. I actually need to know what my velocity is at theta is equals to 90 degrees ताकि मैं कहीं आगे चलूं, क्योंकि मुझे फाइंड ही ये थीटा इज इक्वल्स टू 90 डिग्रीज पे करना था ना. So I have to take a little pause right here. I can't progress any further. मतलब ये मुझे ये velocity निकालनी ही पड़ेगी. Which is why I'm going to come back कि मैं इधर जो I just started to make some headway. Is that clear to everybody?
Yes, ma'am.
Yes, ma'am.
Okay, so let's come back to our third kinematic equation which we were just about to start to use. अब इसको देखते हैं, इसके अंदर मैं substitute करती हूँ. मेरी A tangential जो है that's g cos theta. And now g cos theta ds would be equal to v dv. यही आ गई मेरे पास. And now I can integrate, let me try to integrate this expression ताकि मेरे पास velocity आए. Now the right hand side is all well and good. Again it's just v dv है ना. तो v dv का मतलब हुआ ये 0 थी initially और फिर ये जा रही थी v तक. लेकिन इधर क्या करूं? इधर I'm trying to integrate theta with respect to ds.
ds की जगह dr थीटा लग जाएगा.
Exactly right. So this ds is actually we can manipulate this. So for example, what I'm saying is कि I know कि जब मेरा पहले particle इधर से let's say छोटा सा small angle की infinitesimal position change करता है, there's a d theta, then I know कि ये ds कैसे change हुआ है. This ds is just equal to rho d theta, which means I can write this down as g cos theta rho d theta, and on the right hand side integral of v dv going from 0 to v. Lovely. Now this is pretty straightforward because this is g is a constant, rho for our case is just a constant. So what I'm integrating is just cos theta with respect to d theta, जो कि जिसका क्या होता है, integral क्या होता है, sin theta होता है. That's it. So I get g rho sin theta with units of with limits of pi 60 degrees. 60 degree क्या होगा, pi by 3. And then going to 90 degrees, so pi by 2, and here I'll have v squared divided by 2 with limits of 0 to v. So I can solve this. इसमें limits से plug in करनी है. I will leave that up to you guys, and I can find my velocity. जी मोहम्मद रज़ान आपकी आवाज़ सबको आ रही है, प्लीज़ अपने आप को म्यूट कर दें. अब ना करें, मैं करती हूँ. फाइन. Finally, okay. Razan has finally realized that we can all hear him. Right, coming back. So I found my velocity, and then I can substitute in जो भी मैंने velocity find की होगी to find my tension. ठीक है जी. So this is sorry, t I can find is what I'm saying, not equals to a question mark. Okay, so I hope this example is clear. And कोई question हो तो मुझसे पूछिएगा. So, okay, so the solutions are also in the slides, more thoroughly done. So I'll leave those for you to read through. Okay, now next, okay, मैं हमेशा थोड़ा सा over time जान रहा. How much time have I got left? Have I got any time left? 55. Okay, because some of you were a little late, so I'm going to take 5 more. And to do this one example, because मैंने शुरू ही इस application से किया था कि why do we have those banked curves in for race car driving, or also another example, why does whenever you might have noticed कि जब भी जहाज turn कर रहा होता है, then it never just turns, just staying in that horizontal plane. आपने notice किया है कि वो जहाज हमेशा tilt करके, ये मेरा जहाज है, sorry, वो tilt करके turn करता है, right? I think you all have noticed this. So there's actually a reason why these we employ these banked curves and this sort of tilting motion when we're going around a curve. Or I hope this example will make it a little bit clear. Okay, so we've got a vehicle which is designed to combine the feel of a motorcycle with the comfort and safety of an automobile. If the vehicle is traveling at a constant speed of 80 kilometers per hour along a circular curved road of radius 100 meters, determine the tilt angle theta of the vehicle so that only a normal force from the seat acts on the driver. Neglect the size of the driver. Okay, so it's going in a circular curved road. मतलब ये कि अभी तो मैं इसको सामने से व्यू कर रही हूँ ना, whereas if I look at it from the top, like ऊपर से देखूं, let's say, and if I look at it from the top, it's going through some sort of a curved motion. Let's say वो भी यहाँ कहीं है, और उस curve का I know center of curvature क्या होगा? It's rho. It's given to me. It's 100. Radius is a 100 meters. Right, perfect. Or it's going with a constant speed of 80 kilometers per hour. Nice. So now अब मुझे ना, I'm going to solve it again using my NT coordinates. और अब let me start to define my coordinate system. So I know कि अगर वो let's say इस direction में जा रहा था, ये the man in that motorcycle, then I know कि उसकी tangential direction तो ये हो गई. This is my u tangential, and I know कि my normal must be pointing in towards the center of curvature, so this is my u normal. Okay. Now, अगर if I look at it again from this side view, फिर जो tangential direction है, that's coming out of the page, right? मतलब वो तो इधर से इसको देखते हुए मेरी तरफ आ रही है या आपकी तरफ आ रही है. It's coming out of the screen. Whereas the normal direction is going to be pointing towards the center of curvature, जो यहाँ कहीं होगा या जैसे. So this is my UN direction, and my tangential is coming out of the plane. And finally, वो अब हमारे पास वो binormal direction का थोड़ा सा play आना शुरू हो गया, which is going to be the perpendicular to both UN and UT. So this is my binormal direction. Right? So now what do I have? I have, of course, my equation of motion, which implies that summation F Ft is equals to MAT, summation Fn is MAN, and then finally summation Fb will be equal to what? 0. It's not going to move up and down or anything else. So, or yeah, the way it's just going on this curved path in this plane. Okay. So abhi let's start to take a look at this. So tangential ka I know it has a constant speed. अब मुझे ये भी चीजें लिखने हैं. So I know that my rho is 100 meters. I know that my velocity is 80 kilometer per hour. But I also know that it's a constant speed. So my v dot is equals to 0. Right? So ये a tangential, ये तो होता है v dot. This is equals to m v dot. And this one is equals to mv squared divided by rho. So ये तो 0 है और this just disappears. I've got nothing to do with so tangential direction की forces are just 0. Probably because he's not sort of उसने engine को वो gear up करके, he's not increasing his speed. Fine. But he is changing his direction. So there is a normal force की direction which we need to consider. So now let me draw out his free body diagram. So clearly he's going to have a weight acting straight down, mg. But then let's think about this. अब आते हैं जरा important बात पे. We bank curve होने की बात के why is this automobile for this sort of the feel of the driver tilting in this direction? अब अगर वो इस तरह tilt हुआ है तो उसकी seat जो है वो tilt हुई हुई है at this angle theta. Such that the normal force that's acting on the person is actually going to be in this direction. Theta. ये normal force आ रही है. Why? Because as I said, वो it's tilting like so. ये देखें वो tilt हो गया पूरा थोड़ा सा. तो वो जो normal reaction provide करना है ना इस बंदे के ऊपर, let's say, then that's going to be something like this. Finally, I will अभी I know कि उसने कहा है कि determine the tilt angle theta so that only a normal force acts from the seat. मतलब ये only a normal force from the seat, no friction. लेकिन let me just include the friction just in there, just ताकि we can see whether what effect friction would be having. I'm actually trying to think if friction की direction क्या होगी. So friction will of course suppose their relative motion. Actually मैं इधर कुछ गलती करने लगी हूँ, इसलिए मुझे friction की direction क्या होगी? Will it be in this direction or in this direction?
Negative.
Okay. I'll think about the friction in just a few moments. Just ignore it. Intuitively.
Negative UN नहीं होगी.
नहीं, UN कहाँ है? UN की तो direction ही बिल्कुल, UN तो ये रहा इस direction में. UN
Negative UN पे होगी ना?
नहीं.
फ्रिक्शन कहाँ से आ गई?
ये जिसने पूछा फ्रिक्शन कहाँ से आ गई, पिछले 2 मिनट जो मैं बोल रही हूँ वो कहाँ गए? मैं आपसे ये पूछ रही हूँ. फ्रिक्शन यहाँ से आ गई कि आई एम आस्किंग यू जस्ट टू कंसिडर इट फॉर अ सेकंड, और उसके बाद नाउ आई एम रीअसेसिंग कि whether I should or not. Please pause, remove the past 30 seconds and let me clarify again. So please keep yourselves muted. Don't have much time left, right? So the question is telling us that we have to consider the case when there's only a normal force from the seat on the driver. मतलब ये कि ये जो seat के ऊपर बैठा हुआ बंदा, this is my particle, और इससे जो force seat लगा रही है, that's just the normal force. No friction between the person and the seat. So this is my actual free body diagram for this particular problem. But once we've solved this problem, then I'll come back to consider the case of friction. Okay? Because asal mein that will also that plays a part. There's a reason why I want to bring it up. Give me 5 minutes and then we'll see. Okay, so abhi ka to free body diagram ban gaya na. Let's start to plug things in. I do need to change my color again, just to highlight ke okay, this is my B direction and this is my UN direction. When I'm resolving my forces in the normal direction, then what do I have? I have an n ka component, which is n sine theta, right? Or weight ka koi component normal direction mein act hi nahi kar raha. But I do have a component of the normal direction, normal force acting in the normal direction. Why? Because this seat or this automobile is inclined at an angle theta. Okay, इसकी incline होने की वजह से ये एक n sin theta n का component आ रहा है normal direction. So n sin theta is equals to mv square divided by rho. This is my equation of motion in the normal direction. Now let's also sum our forces to 0 in the binormal direction. And in the binormal direction, I just have n ka component n cos theta acting upwards. So this acting upwards one is n cos theta. which will be equal to directly this mg acting downwards. Okay? So I'm getting that my normal force is mg divided by cos theta. Right? So let me substitute this into my expression for my normal forces. I get mg divided by cos theta multiplied by sin theta is equals to mv squared divided by rho. Is that right? So m and my m cancel out. Instead, I'm left with tangent theta, sin theta divided by cos theta is tangent theta, is equals to v squared divided by rho g. ऐसा ही है. Now v, I know it's traveling at 80 kilometers per hour. Rho, I know is 100. G, I know is the constant of acceleration. So I can solve this to find what my theta would be. So now this is a little interesting. Why? What's happening? अब इस थीटा का मतलब ये है कि at this theta, अब एक तो पहले I want to go into the physical meaning of all of this. Just अभी I'm going to give you 10 seconds please to ask अगर किसी को ये वाला समझ ना आया हो कि अभी तक क्या हो रहा था कि equation of motion हम use कर रहे थे. What was happening here? ये थीटा की वैल्यू आएगी किस तरह? Is everybody clear on that? Yeah, not so much. Anyone? No. Okay. So now let's start to discuss this. Now, please notice that whenever something is going in a curve, जिस तरह के this car was going in a curved direction, right? Then there would have been this centripetal acceleration. मतलब ये this an वाली towards the center of curvature एक acceleration हो रही है, right? Which is causing the change in direction. Now, of course, अगर centripetal acceleration है, then there has to be a force to cause it. ठीक है? So अभी हमने जो particular analysis किया ना, इस case में we've seen कि that force is being provided by a component of the normal reaction. Or at this angle theta, then this force is enough, basically. The normal force is enough to provide this centripetal acceleration. Consider the case, अगर कि ये actually theta पे ना होता और instead हमारे पास हमारा बंदा सीधा सीधा एक सीधा flat horizontal उस पे बैठा. Then in this case, the normal force is just balancing the weight mg. तो मतलब ये कि नॉर्मल का तो कोई कंपोनेंट ही नहीं था, विच मीन्स कि हमें इस डायरेक्शन में कोई और फोर्स चाहिए. और व्हाट इज दैट फोर्स व्हेन दिस वुड हैव बीन हॉरिजॉन्टल? एग्जैक्टली राइट, इट वुड हैव बीन फ्रिक्शन which would have provided it to us, such that if I was just sitting horizontally, if this thing had just stayed in with no banking angle, then I would have needed sufficient friction to provide sort of the force ताकि मैं भी गाड़ी के ही centripetal acceleration से move कर सकूं. ठीक है? So by अब उसके साथ इशू क्या है? अब इशू ये होता है कि कभी कभी ऑब्वियसली फ्रिक्शन की एक कुछ लिमिटिंग वैल्यूज हैं. अब अगर हम रोलर कोस्टर्स पे बैठे जो घूम रही होती हैं गोल गोल इन अ सर्कल, then you might have noticed that their seats are sometimes they're made of plastic which has very low coefficient of friction. Exactly इसी वजह से ताकि हम लोगों की friction is so low such that the friction is not enough to provide the centripetal acceleration. ठीक है? So उसकी वजह से क्या होता है? We start to slide outwards. We sitting on the roller coaster. Similarly, अगर गाड़ी पे ऐसे ही हो और एक कोई बहुत गाड़ियों में भी ऐसे ही हमारे साथ हो रहा होता है कभी कभी when somebody is taking a sharp turn and there's not enough friction then क्योंकि हमारी speed इतनी ज़्यादा थी, V was so high, then we start to slide in our seats, don't we? इसी वजह से because that friction is not enough to provide my centripetal acceleration. So that's what this example is showing you. by having this angle theta, जिस पे अगर मोटरसाइकिलिस्ट इसीलिए थोड़ा सा इस तरह करके टर्न होके करते हैं, या फिर by having your airplane go at an angle theta, then we ensure कि हम friction की dependence कम कर दें, और कम टू दी एक्सटेंट कभी कभी हम इतनी भी कम कर सकते हैं. फॉर एग्जांपल इस एग्जांपल में हमने देखा कि अगर हम थीटा पर्टिकुलर वैल्यू का चूज करें, देन वी डोंट इवन नीड एनी फ्रिक्शन एट ऑल, राइट? So we can completely eliminate any dependence on friction. We can just ensure कि just the normal force से ही हमारी centripetal acceleration cause हो जाए, और हमें कोई sliding इस तरह cause sliding होएगी ही नहीं फिर, क्योंकि the normal force is enough to do that. ठीक? That's why airplanes turn in that way, ताकि जो customer जो passengers बैठे हुए they don't slide on their seats. So I hope this was an interesting example for you all. Please, again, as with always, we're talking about things which you need to ponder over afterwards too. And I've already taken up 10 minutes extra. So there is also another example, and I'd like you guys to go through it if you get a time. But otherwise, we have 2 hours tomorrow. So inshallah, I will go through example 3 tomorrow before we start our r theta coordinate.